Thank you very much for joining us. In this webinar, we wanted to explore together with you the kind of the evolution that keyless entry systems went through from our eyes as security researchers. My name is Shaked Delarin. I'm a security researcher at Argo Cybersecurity. I'm in the company for almost 4 years now. And together with me presenting is also Shachar Schechter, which is a colleague of mine, also a security researcher in our team. And what we wanted to kind of explore in this webinar is kind of what drove, what really drove the keyless entry systems to advance from our perspective as security researchers. So as security researchers, we are getting a lot of these BCMs, smart access systems, to audit from the eyes and the perspective of a hacker, of a thief. And we wanted to share with you some of the insights that we have noticed that manufacturers are using correctly and incorrectly. So to start at the beginning, I will hand it over to Shachar to kind of start to describe where it all started from. So, Shachar.
Okay, thank you, Shaked. Yeah, so we are going to go today over 5 different technologies: the remote keyless entry, passive keyless entry, BLE proximity authentication, NFC, and finally ultra wideband. So let's start. The first one would be the remote keyless entry, which is kind of the first key fob that we are all familiar with. And we have keys on this key fob. When we press the unlock button, it transmits some kind of signal. The car processes the signal, verifies it, and unlocks the door. So let's consider a simple implementation where the same unlock signal is transmitted over and over again. In this case, an attacker may record the signal and replay it at a later time. And since it's always the same signal, he is able to unlock the doors and enter the car. So to mitigate this, we need to make sure that the signal transmitted by the key fob is always different. And we do this using something we call rolling code. So we have here some kind of an example of an implementation for a communication between a key fob and a vehicle. And in our protocol, we will have 1 byte for the command, 0 for unlock, 1 for lock, and 4 bytes of rolling code. The rolling code would be generated using some kind of cryptographically secured pseudo-random generator. So that means that the rolling code is not predictable. Only the key fob and the vehicle knows what would be the next rolling code. And so when we press the key fob unlock button for the nth time, for example, it will transmit rolling code XN, and the vehicle, if this is the expected code, will unlock the doors. So let's verify that replay attack is not feasible right now. So the user presses the unlock button and transmits unlock signal with rolling code XN. And since it's the expected code, the doors would unlock. In the same time, the attacker will record the signal. And so the attacker knows rolling code XN. Later, the attacker will go back to the car and try to transmit the recorded signal. But since the car already received rolling code XN, it now expects rolling code XN plus 1. And so it will reject the signal and the doors would stay locked. So replay attack is not feasible after applying rolling code. However, we can consider a different type of attacker. And in this case, the attacker will be able to also jam the signal while recording it. So jamming basically means that the car does not receive the signal, and we can do this by transmitting at the same frequency of the key fob, for example. So let's see what the attacker can do. So the user presses the unlock button, and we have the 0 byte, which indicates an unlock signal, and the rolling code X1. The attacker will jam the signal and record it. So the door stays locked, and the user is a little bit confused. Will probably press the unlock button again, and this time the key fob will transmit the second rolling code X2. And again, the attacker will jam the signal and record rolling code X2. And immediately afterwards, we can take the first recorded signal with rolling code X1 and transmit it to the car. So X1 is the expected rolling code. The doors would unlock, and the attacker still has rolling code X2. So the user enters the car, drives around, finally returns, park the car and lock the doors by transmitting rolling code X3 with a byte of 1, which indicate lock. So the attacker will again jam the communication and record the signal, record rolling code X3, and take the previously recorded signal, rolling code X2, modify the unlock signal to a lock signal by simply modifying the 0 byte to a byte of 1, and transmit this to the car. So X2 is the expected rolling code, and so the doors would lock, the user will go away, and finally the attacker may go back to the car, take the last signal we recorded with rolling code X3, modify this lock signal to an unlock signal, again by modifying the 1 byte to a 0, transmit this to the car and unlock the doors. So what we can learn from this? So it's problematic if the attacker may take different signals and reconstruct new ones. We don't want the attacker to be able to create new signals that the car will process. And to prevent this, we can add some kind of a signature to the end of the signal, which will sign on both the command and the rolling code. And this means that we can't really modify the command to a different byte because the signature will not be correct. Another option is to encrypt the whole message, and we will get the same result. Okay, so let's summarize the RKE. We talked about two attacks, the replay attack and the roll jam attack. We want to apply rolling code to protect against the replay attack. We should sign and encrypt the messages transmitted transmitted by the key fob and verify those on the car side. And finally, we would also like to talk about rollback attack, which is kind of a newly discovered attack from 2 years ago, I believe. And it's an example that still some kind of bad implementation may result with different variations of the roll jam attack. Okay, so let's move on to the next technology, the passive keyless entry system. And in PKE, the communication is passive. So this means that we don't need any interaction from the user. The key fob and the vehicle communicate with each other without any interaction. And basically, the car transmits some kind of a random challenge. The key fob generates a response using some kind of a strong cryptographic algorithm. And since they share the same secret key, the vehicle may verify the response and unlock the doors or start the engine. And let's assume that the challenge is also generated using a good cryptographic function. Okay. So the first attack is called the relay attack. And in this case, we have two attackers that work together. So let's see a video, an example of what they are doing. Skip ahead. Okay, so we have two people here. Each of them has some kind of a device, and they communicate with each other. One of the attackers stays near the car, the other one goes around the house, trying to get as close as possible to the key fob, and finally, they can enter the car. And then they can do the same to start the engine. So they need to do this because the PKE itself doesn't work for long distance, because otherwise, even if I'm at my house, then someone may come to the car and open the doors. So the relay attack basically tries to overcome the distance limitation and still unlock the doors. And this is the result of the communication being passive. So let's close this. Okay, so what happened here? So we have one attacker near the car, the other one is near the key fob, and attacker A triggers a challenge from the car. It usually happens when you try to open the doors, for example. So attacker A forwards the challenge to attacker B, which transmits it near the key fob. The key fob will generate a response because everything is passive, and attacker B will forward the response back to attacker A, which transmits it to the car. And this way we can overcome the distance limitation. So what can we do? First mitigation may be to measure the time between the transmission of the challenge and the reception of the response. This is called the round trip time. And basically, by putting a constraint on this value, we can estimate the distance. So it's nice, but in the standard PKE technology, it's not really good enough to get high accuracy. And we have ultra wideband, which comes forward to solve this kind of issue. But we will talk about it later in this presentation. Next mitigation is to add RSSI to the packet, to the transmitted response by the key fob. So the car would have multiple antennas, for example, 4 or 6. Each of those antennas will transmit the challenge, and the key fob will measure the RSSI, which is basically the strength of the signal, and sends it to the car. The vehicle will receive these RSSI values of all of the antennas and use this to estimate the location of the key fob to see if it's inside the car, near the door, and so on. So is it good enough? It's good, but still has some issues. So we can consider an analog attacker, which basically may transmit the signal at a higher strength. So attacker A will forward the challenge to attacker B. Attacker B will transmit the challenge with higher strength. And so the key fob will calculate different RSSI values, which corresponds to being closer to the car. And so those values will be processed at the car side, and since they show close proximity, the doors would unlock or they could start the engine. Second attacker, a digital attacker, may demodulate the signal and modify the RSSI values. So since the key fob does not sign the RSSI values that it transmits, we can just modify them, modulate the signal, and transmit the car the modified signal with better RSSI values, which indicate close proximity. And finally, third mitigation is to integrate a motion sensor. And the idea is to make sure that if the key fob didn't move for a while, for example, it's on the table at my house, then it will stop answering on challenges. So, for example, after 1 minute of idle time, even if the key fob receives a challenge, it will not respond until it is moved again. And it's a way to mitigate the issue without actually solve it. But I really like this solution. Okay, so let's move on to the next attack. And we call this the one-man relay attack. So originally, I said that the challenge should be generated using a good cryptographically secured pseudo-random generator. And so we can consider what happens if this is not the case. So for example, if the challenge is predictable, if it's just an increment of the previous challenge, or if you're using an LCG or LFSR to generate the challenge, then we might have the one-man relay attack. And it goes like this. So we have only one attacker, and he goes to the car and triggers a challenge, and it predicts the next challenge. What would be the next challenge when it will go back to the car? It transmits this challenge, this predicted challenge, to the key fob. The key fob will respond, and so the attacker may go back to the car, trigger another challenge. If the new challenge is the predicted challenge, then we already have the response. We can simply replay the response recorded from the key fob and unlock the doors, then do the same to start the engine. So we have two ways to mitigate this. Each of them is good. So the first one is to really make sure that the challenges are not predictable, to use a good CSP RNG with high entropy seed. And another option is to sign the messages, the challenges transmitted by the car. And so even if the challenge is predictable, the attacker can't really send the challenge and receive a response from the key fob because he can't sign the challenge. Okay, so let's talk about the key points from this part. We talked about the relay attack and the one-man relay attack. We want to make sure that we are using a good random function with high entropy seed. RSSI values should be signed or encrypted. We want to apply motion sensor in key fobs. And it's also worth considering to sign the challenges sent from the car and verifying those on the key fob side. Okay, so now we kind of change the hardware. We don't really need a key fob anymore because everybody has a smartphone in their pocket. And so we want to start unlock and start the engine of the car using our smartphone only. And in this case, we have different technologies. One of them is BLE, for example, and the other one is NFC. And so they both work similarly to the PKE. We have some kind of a challenge transmitted and a response generated. In BLE, we still have the RSSI values, which are transmitted. And so the analog attacker we talked about previously still works. We have an example of a relay attack on Tesla. And for NFC, we also have the same relay attack issue. However, the technology makes it a little bit harder because we need to be really close to the key fob and to the car. And this is kind of a limitation of the technology itself. Anyway, what's really good about using a smartphone for BLE and NFC is that if we have some kind of a security issue, for example, it's really easy to upgrade the application on the smartphone to kind of try and mitigate the issue. And in the case of the physical key fob that we usually have, it's a little bit harder. Okay, so from now on, we will move to ultra wideband, and Shaked will continue.
Thanks, Shahar. So we now understand that key fobs are good. They were here with us for a long time, for many years, but it's time to kind of advance towards having our keys in our phones because it's more convenient, because it could be passive, because it could also be updated in a much easier fashion than what we have with key fob. So the first step towards that, as we believe, as we see it right now, is a consortium called the Car Connectivity Consortium, the CCC, Digital Key Standard. Basically, this defines how we are going to use all of these technologies and use them in our phone in a fashion that is completely agnostic to any operating system, and in the future, hopefully for any other car. So when you have a digital key signed on your phone, it could be used for this car or for the other car. It could be Android, it could be iOS. The consortium has really gathered the phone manufacturers as well as car manufacturers together, and this is a very interesting and cool project. The architecture that it defines is also quite comprehensive. It's not only just uses a single technology to communicate, to define the communication between the device and the vehicle. There's also backend involved, and there's also the ability, by the fact that you have your digital key on your phone, it could be shared with a friend. It could be shared with, if you're on a rental service, the digital key could reside on your wallet app for this amount of time, and then it would be revoked. So everything is defined in the standard in a pretty comprehensive way, and this is kind of how this is kind of what the future holds for us, it seems. So how is that going to be really implemented? Because so far we heard about these technologies which are good but also kind of flawed, and this is where ultra wideband comes in. We heard about it mostly from the iPhone or the AirTag, which most of us have heard about it, but it's also a very good solution for automotive purposes. And the reason for that is that it provides not only better security, but also better ranging accuracies. At the same low energy cost that we have gone used to when using key fobs or BLE or NFC for that purpose. And the reason for that, the way that differentiates ultra wideband from these other RF protocols is the fact that ultra wideband, as its name suggests, uses an ultra wide band for the communication. For the modulation of data is actually happening over pulses, which occur over a very large bandwidth. This allows a very good bandwidth and very high speed, and also by that we can have much better accuracies when we are reporting our range. But how does ranging really work in ultra wideband? So the difference between ultra wideband and the other ways of measuring via RSSI and all of that is the fact that we are using time of flight measurement, and the way to do that is to exchange a few messages between what is called an anchor and a tag. The names are not really that important. It's just two parties that want to understand how far one is from the other. And if we measure the time of flight that a single packet takes for the signal to be from the time of transmission until it is received, we can understand the distance between an anchor and the tag. And if the positioning is based on time of flight, it is not based on a signal strength. There is no relay that could be involved here, and this is why a relay attack is not necessarily applicable here. However, when we come to think about it in this architecture, then we might think, well, what really makes ultra wideband secure in this architecture? Because If we are just exchanging messages, can't an attacker do the same? So actually, the latest revision of the ultra wideband standard, the OE2 41140, does define a new concept into the data that is transmitted in the ultra wideband packet called a scrambled timestamp sequence. This is similar in the concept of a rolling code, but it is defined to be cryptographically secured. It is a pre-shared secret that is shared between the two parties that could be shared not in a ultra wideband communication session. It could be transmitted and it could be exchanged in a BLE session, which does provide the security we need. It could be pre-shared during pairing. So we have two parties which are sharing the same secret value, and the STS is derived from that secret value, from that secret seed. And since this is cryptographically secure, then the next STS that is generated every time is very, very difficult to predict. And the usage of AES and the AES and the secret pre-shared key does make it a lot harder for an attacker to kind of spoof this kind of message. So can't this be attacked? Not in a practical way. When a ranging session is being, when there is a ranging session between an anchor and a tag, this is the data that is transmitted between them. There is actually no raw data that is being transmitted during that time, only the STS. And the reason for that is that during the ranging, we want to be as accurate as possible. We don't want to transmit more data than we need to, and we just need to make sure that that they are somewhat secured. In order to secure them, then we will have to add the STS there. Ultra wideband does allow for arbitrary bytes to be added to the packet, but this is not necessary during a ranging session. It could be necessary, and it could be very useful that after the single exchange happens and we want to share the time recordings of the received packet here and the received packet there, then we could exchange data, which could also be encrypted. But for the ranging, we are only using STS for that. And I apologize, I made a mistake. The standard is 802.15z and not what I said previously. So the ultra wideband is defined in this IEEE standard. So this is the packet that is being transmitted and it's being received on the other on the receiver. And what's interesting here in ultra wideband is the way that this is compared. So we are sending a secret value, not a secret value, we're sharing an unpredicted value, the STS, and we expect the receiver to check whether the STS is what it is expected to receive or not. And the way to do that is not actually to do that in a bit-by-bit fashion. We do not demodulate the signal and digitally compare the STS with what we expect. For performance reasons, in order to have to do that quickly, we are doing what is called a channel impulse response, which briefly speaking, it's much more complicated than it sounds, but briefly speaking, it compares between the analog signal that is received, that's been received, and the analog signal that we expect to receive. And we are doing a correlation between these two signals, and this correlation changes over time as the signal is received. So when I'm transmitting just random data that is completely unrelated and it's not even in an ultra wideband structure, it makes no sense, then the correlation between noise and the expected signal would be low. However, once the true signal is being received, then this would mean that there would be a high correlation peak when this signal is received. One more thing that I would like to mention before moving on is the fact that if you look at the graph here, you would see that yes, once I identify a highest peak, okay, I receive a highest peak, then I would know, okay, this is the best correlation that I received in a long time. However, due to sometimes we have a line of sight limitation. A line of sight could mean that our signal is transmitted in the air, but over, for example, a brick wall, or something else that would diminish the strength of the signal as it is received on the receiver. This would mean that a legitimate signal could be received at the receiver. However, in the correlation, in the power analysis, it will have a lower correlation peak than the other signal that was received, which could have been received in by some reflection, by some other means. And for that purpose, the standard does acknowledge that, and we have to be accurate here. So when we receive the strongest peak that we noticed, we are looking back at a specific window to look for other correlation peaks, which could mean that these signals was received there. We have to define a threshold, we have to define a search window, but once we define them, we would know where to look and maybe say, okay, the signal was received not at this time, it was received earlier. And that would make our ranging sequence much more accurate. So that is the system that is currently being performed, and there's actually a way to kind of exploit it. So there is this work by ETH Zurich, which was published in 2021, originally in NASCAR and also in Usenix. So it is called GhostPeak. You will see why in a moment, and it was the first paper to present a practical distance reduction attack on exactly this mechanism. So on ultra wideband ranging with STS. So what the paper suggests, the basic principle of this attack is the fact that this comparison of the STS is performed with this correlation analysis. So if you get a peak, okay, then you are looking back to see if there's another peak that was received before. And it could be, in many cases, in many times, this is really the case. However, they found that if they somewhat generate a signal that, since they do not know the STS, they will use the same structure of the signal with a random STS. However, they will be transmitting it at the same time, kind of interfering with the real signal. This would, if you think about it, it will generate some kind of noise into the correlation computation that is being performed on the receiver. This would mean that eventually this is not, the STS is not checked digitally. It is checked with a correlation analysis. So if we are able to somewhat introduce some noise into this computation, the receiver would sometimes falsely see, when it looks back for previously received peaks, it would maybe receive, due to noise, it will maybe receive a fake correlation peak, or a ghost peak, if you will. So and by some chance, this ghost peak could be determined to be received earlier. So earlier than the real signal that was received. So eventually the receiver will think that the target is much closer to it than it really is in the air. The result of the paper were actually very impressive. For example, the NXP SR150 was checked with an iPhone, and the attacker device was placed really close to the iPhone, and they actually managed to reduce the distance measured on the iPhone from 8 meters to 0. And so practically, it's really impressive. But we have to remember that the attacker doesn't have control, since this is all probabilistic. This is all based on the correlation hit success that you are able to get on the receiver. You never control the amount of meters that you take off the real measurement. You also cannot determinedly succeed in the distance reduction, because again, this is all random. So based on the results presented on this paper, which is impressive which is completely impressive nonetheless. The highest success rate that was able to achieve was around 4.25%. So still impressive, but it is not 100% deterministic attack that would work every single time, such as the relay attack or a replay attack on an RKE that is completely reliable. And add to that the fact that you do not always control the amount of distance that you reduce. So add that. So Ghostpeak is a very important landmark in this context of ultra wideband. However, we wanted to look at it from an automotive perspective because we get to see these systems that are implementing ultra wideband as kind of a solution for secure ranging for automotive. And this specific paper did not test this on receivers which are designed to be for automotive manufacturers, which sometimes they are just not available to the public. These are specifically designed for OEMs, specifically for tier ones, and they are not really sold. They're not really sold on DigiKey for regular customers. Also, if we come to think of some kind of a mitigation in terms of architecture, like how would we design our vehicle in a way that will not be completely vulnerable to this kind of attack, then we have to remember what this attack is really about. This is an indeterministic attack that works sometimes, but definitely could work. It could definitely hit our receiver. So, but when we design our vehicle, we were most likely not going to use a single ultra-wideband receiver. We are probably going to spread them out across the vehicle to triangulate exactly where is the owner of the car is actually located. This could be for convenience reasons because we want to unlock this door or that door. We want, or maybe the back door. And also, so that means that if we are able to attack, like we are placing attackers on all of the antennas, let's say that this is 4 ultra-wideband antennas, then we would have to hit all of the 4 at the same time, which reduces the probability of something like this to succeed. But let's say that we have to remember that if we design our system that way, we are all of the antennas are feeding continuous data into the central ECU that eventually decides what to do with the ultra-wideband measurement, with the ranging measurement. If this is a continuous stream of data, then a single hit of 4%, 2%, 3% success rate could be ignored when we are looking at a moving average, for example. If this is some other more complex computation, then a single drop in the measurement could be discarded as noise, and it could be discarded by the ECU. Not to mention the fact that we have to keep these attacks in mind when we are designing the code of the ECU to not only ignore that as noise, but maybe think about it as an attack. So this is kind of how we see it. It could be like an architecture that is somewhat proof to this specific attack, which we know could have an effect on ultra-wideband devices. So to kind of conclude what we had so far is we know that keyless entry systems are very convenient, but they have been vulnerable to security breaches all the time. And it's very difficult to replace them, obviously, because a lot of the vehicles that we have today have been designed and manufactured a long time ago. But despite this technology, despite these advances in technologies, in ultra-wideband and BLE, this can introduce vulnerabilities, not only in the distance reduction attack. If we are introducing more complexities, if we are introducing more software above ultra-wideband, above BLE, then we have to make sure that programming vulnerabilities will not find their way inside our code. And sometimes even these minor flaws could have a very serious impact on the system, because eventually today we see automotive manufacturers take the fact that whether an attacker can unlock our vehicle, they take it very seriously. And I'm sure this forum is aware of this situation that the industry is going through right now. And eventually, we believe that as we are performing penetration tests on these kinds of systems, the smart accesses and the BCMs, eventually the OEMs are starting to look for these high-end solutions and really improve their systems. So eventually, security assessments, we do find them helpful for these automotive manufacturers, even if they think they follow all of the standards, they know that everything is secure. They are using the latest technology. They are using ultra-wideband. You can always find pitfalls here and there. So, so as mentioned, we, myself and Shahar, we are both security researchers at Argos. We are an automotive cybersecurity company with offices in Germany, in France, in US, in Japan, in Korea, all over the world. We were founded in 2004, and we have been focusing on automotive pretty much ever since. We have a lot of partners, of OEMs and tier ones that we are working with, and together we are protecting over 72 million vehicles. And our portfolio includes in-vehicle intrusion detection, prevention, fleet monitoring, XDR platforms, and also a secure development platform that we help our client build better products and build better code. So our group, the consultancy group, is the services group. We provide penetration test services for OEMs and tier ones. We help them not only comply with the security compliances of CSMS and the type approval, but we also help them in the initial stages of security architecture and design, and also testing, which is what we do, the implementation once the ECU is ready to go to the road. So we look for security vulnerabilities, these errors in implementations, and eventually we introduce an attacker that wants to hack the ECU from our eyes, from the eyes of from an attacker, and we help our clients eventually just make the product better. And we do that because we like to break stuff, and that's always fun. Thank you very much for joining. Thank you very much for hearing us. And have a good day, good evening, depending where you're located.
Thank you everyone for joining. I hope it was helpful and informative.